everyone. Today we're going to continue with nucleophilic aromatic substitution reactions. We're going to go through the same mode. Give me just a second. Let me bring back my screen. Okay, we're going to look at elimination addition reactions with a substituent and the leaving group on, and our substituent this time will be an electron donating group. So let's take a look at its effect. As we already have learned, the electron donating group is going to give electron density to your ring. And if we are observing the ring as an electrophile, that excessive amount of electron density is not appreciated at all. Okay, so let's just pick up a benzene ring, which already has an electron donating group. So let's put a good electron donating group on, a methoxy group, and we will have a leaving group on ortho, para, and meta position, and see what will be the outcome of such reaction. So we'll start with the ortho position. Let's put a good leaving group on, chloride will suffice, and let's add sodium hydroxide. Again, don't forget your lone pairs, your charges, and we're going to perform an elimination addition reaction. So as we remember, this reaction happens under high temperature in the presence of a strong nucleophile that can also act as a base. So first, your hydroxy group is going to pick up the proton, and we will kick out chloride. The byproduct of this reaction will be sodium chloride and water, which we will use later on. Okay, so as a result of this reaction, we have learned that already. We will form an unstable intermediate benzene. And it will be reacted with the hydroxy anion. So just like in the previous example, that hydroxy anion could attack either ortho or meta position. So let's think about it from both perspectives of proceeding with the reaction: steric effect, electronic effect. If we're looking at steric effect, putting hydroxy group on the ortho position at this point is going to have an effect on the existing electron donating group in a close proximity. So that is one of the reasons that hydroxy group would not like to go there. But what will happen electronically if anyways we'll place the hydroxy group on? So let's go ahead and do that and try if we can do it. So if we put hydroxy group, attack the ortho position, the electrons are going to move around, and they will stop right on the carbon that carries electron donating group. So the result of such arrangement will be the following. And you know, every time you end up with electron pair next to electron donating group, we like to emphasize the presence of this electron donating group by putting those lobes around your lone pairs to identify their steric bulkiness. Okay, so let's pick up on our bonds here. So we formed this intermediate with the negative charge right next to the lone pairs of electrons on oxygen. And as we can see from this drawing, it's not a very comfortable situation. So the electrons will rush back and end up right where they started at. And that is not a good place. Okay, so this is unstable and unfavorable. Okay, So then the other alternative here will be, I'm going to withdraw that intermediate first, the benzyne intermediate. Our other alternative will be if we attacked the meta position. So let's see what will happen in this case. Let's take a look at that. We will attack this position. The electrons will roll around. And as you can see, guys, there is no way they can stop on the carbon that is carrying methoxy group. They're going to roll from that position round and around, and they will end up on this carbon, which is away from your carbon with the oxygen on. So the result of this arrangement is going to give us the following. And just to be fair, we're going to place the little lobes around our oxygen, so we will see the proximity of the lone pair of electrons on carbon in that case. So we've placed hydroxy group on the meta position, and now we have a double bond here, double bond here, double bond over here, and the lone pair of electrons on the position that is far away from the alkoxy group, okay? So it looks like your meta substitution is favorable and more stable. Okay, so this was the unfavorable ortho substitution, and meta is better. Can we say that it's a great case? Absolutely not. It's not a good case because we are going to form a very unstable intermediate to begin with. Our electron donating group is pumping electron density into, oh, I keep on turning this off. What is wrong with me today? Electron donating group is pumping electron density into the ring, so it's not a good case. But ortho is horrible and meta is just tolerable, okay? So we're going to continue with this motif, and this time we're going to place the leaving group onto meta position. So let's do that. We're going to start with the same substrate. Oops. But this time, the leaving group is on the meta position. So here we started with the ortho substitution original. Now we start with meta substitution. And let's see what our expectations would be. Again, just like in the previous case, first we're going to obstruct a proton on the adjacent position with the hydroxy group. Has a dual job here. It acts as a base and also as a nucleophile. So chloride leaves, just like in the previous example. Let's not forget the reaction conditions, be organized, okay? And so we're going to form our intermediate, just like in the previous case. Guys, if you compare this intermediate and this intermediate, they're identical. And we already have learned that ortho position is unfavorable and meta position is a tolerable one. So I'm not going to repeat the mechanism because as we can see, we formed the intermediate exactly in the same place. So take home lesson that when we start with electron donating group and the leaving group are ortho to each other, our favorable product will be meta substituted product. And when the electron donating group and the leaving group are meta to each other, we're going to end up again with the meta product as the major one. Last thing that we're going to do, we will look at the substituent on the para position. And let's see what the outcomes will be in this case. I keep on forgetting to switch the thickness of my pen. Okay. So now my chloride leaving group is residing on para position. Oops, para. So let's follow up this one arrangement. So again, sodium hydroxide. And this time, we're picking up this hydrogen based on the drawing of the benzene ring. So let's pick that up. Form a triple bond, release chloride. Okay. And so we're going to end up with this intermediate. And as we can see, and I forgot to do the color labeling, so let's go ahead and do the color labeling here. With the ortho substitution, we ended up with 2 eligible positions, out of which meta position was favorable. With meta substitution, we ended up again with 2 positions, out of which the meta position was favorable. And ortho was again unfavorable. And now what we see with the para substitution pattern is that we again will have a meta position and a para position. We already know a little bit about our meta position. So let's see what will happen if we try to run the attack with hydroxy group on the para position. Let's examine that possibility. So this is para, and this is meta. And we're going to proceed with the para because we know what happens with meta. Attack this carbon, electron density will move, and watch this. The electrons again will land on the carbon that is indeed carrying an electron donating group. So the result of this arrangement will be adding hydroxy group on the para position, and we're going to end up with a double bond here, and the lone pair of electrons on the carbon carrying oxygen. Very much the same picture that we saw with ortho substitution. And that's not good again. So we can see that in case of para substitution, with electron donating group and a leaving group being para to each other, the meta position is going to give us the major product. Okay? So the take-home lesson here is that no matter what electron donating group you have and electron withdrawing and the leaving group you have, as long as your leaving group is good and your nucleophile is pretty strong and you have very harsh conditions, your major product is going to end up being substituted on meta position. So let's put that take-home general scheme. Oops. Our little take-home lesson or conclusion. Okay. With the benzene ring carrying an electron donating group on one carbon and leaving group on any position, as long as we have strong nucleophile, and we already know what strong nucleophile is, it's going to carry a negative charge, it's going to be compact, and we have harsh conditions, the nucleophile is going to end up on the meta position. Ortho, meta, para substitution are going to give you meta product as the major product of the reaction. Okay? And now that we have determined that, let's make sure that we continue with the mechanism on any one of those scenarios. And since we already started the mechanism here for the meta substitution, let's just do that right away, okay? So we have a negative charge on one of the carbons. We've removed the electron density from this carbon originally. So we're going to move the electrons back, stabilize, move the electrons back onto this position, blast the proton, or H is on the meta position. So now we have, oops, made the double bond here, and put a lone pair of electrons onto this position. And oops, why did my slides run away? Here we are. And of course, now your water molecule is going to offer a proton. We'll recover hydroxy group. And we will form our product. Okay. So hopefully you've understood this. Now we can put together a couple of examples on predicting the product and predicting the reaction conditions, okay? And we will see if this sits well with you, and then I'll put out a couple of practice problems. Let's open up a new page. So let's run through a couple of scenarios. Let's predict the product type of problems. And now I want to give you a good mix of the problems and see if we can figure out the right solution. Number one. Let's start with this substrate, and we're going to react it under different conditions and predict the products for each set of conditions. Okay, let's take a look at this problem. We have a benzene ring with electron donating group and bromine. We can observe it as electron withdrawing group or as a leaving group based on the reaction conditions. Okay, so the reaction conditions for reaction number 1, we see a clear chlorination reaction. The reaction set prompts us to use electrophilic addition reactions in which your benzene ring acts as a nucleophile. Okay, benzene, nucleophile. So we understand that electron donating group is going to dominate the reaction outcomes. And since your electron donating group is dominating the reaction and it's an ortho para director, we're going to have two ortho positions and one para position available. Bromine is a weak electron withdrawing group. It's going to play no role in determination of radioselectivity of the product. We can see that if we put chlorine over here, it will be repelled by two substituents. If we put it on the other ortho position, it will be next to NH2. And if we put it on the para position, it will be next to smaller bromine. Clearly so. Position next to bromine will be more favorable because it's less sterically hindered. So we're going to put the product together. As EAS product. Okay. So now let's move on to the second set of reaction conditions. We have the same substrate. Very common mistake is that students see electron donating group and they think it's an activator. Yes, it is an activator for EAS reaction. It's a deactivator for NAS reactions. And when I look at the reaction conditions, my reaction conditions for the second set is the NAS reaction. And since the temperature is pretty low, the reaction can proceed only by addition elimination scenario. And as we remember, for addition elimination reaction, what do we need? Your benzene is electrophile, okay? So in order for it to be good electrophile, you need a strong electron withdrawing group. You've got none, okay? And you have an electron donating group. And your reaction is not gonna take place, okay? Don't have electron withdrawing group. Your leaving group is meta to electron donating group, which will not pull the reaction here. So in this case, we're going to have no reaction whatsoever. Now, if we harsh up the conditions, as we did in the third reaction, the third set of reactions is going to be, again, an NAS reaction. But this time the temperature is pretty high. It's elimination addition reaction. And again, as we remember, our benzene is an electrophile. Our reaction conditions are pretty harsh, 350 degrees Celsius. We have electron donating group. We have leaving group, which are meta to each other. And we know that no matter where electron a leaving group resides with electron donating group, the outcomes will always be substitution of bromine, in this case, on meta position, on the meta position. So the outcome of this reaction is going to give us a disubstituted product where bromine is substituted with chlorine. Okay? Oh, with hydroxy group, what is wrong with me with hydroxy group? As a matter of fact, guys, this is a great reaction. Your NAS reactions are great reactions for introducing a hydroxy group to the benzene ring, or introducing the amino group to the benzene ring, when we don't have to go through a whole bunch of reactions in EAS to get those groups on. Okay? I'm going to put out a couple of practice problems for you. So let's see this. And let's see if we can predict the reaction conditions here. Let's see if we can predict the reaction conditions for this particular set. Okay? Always look at the starting material, identify the functional groups on this. In our starting material, we have a nitro group on this carbon. That's the only substituent there. What we can see in the product is that on one of the carbons, we have a nitrile, which can be directly produced from the nitro group. So that is one group that can be identified. And then we have another substituent on the ortho position. Now let's go back to nitro group. My nitro group is electron withdrawing. I'm putting a carbonyl on, so it's definitely an EAS reaction. And with the nitro group on, meta director, deactivator, the substituent is going to go onto meta position. So what do I need to do? In the final product, my nitro group is turned into nitrile, which is also electron withdrawing group. So I need to start with NO2, but then go through the step when NO2 goes from electron withdrawing group to electron donating group, and then manipulate that, send the next substituent, manipulate it, send it to ortho position, and then convert your group on this position into nitrile. Let's try to do this. First, we have a nitro group, which is electron withdrawing group. We're going to convert it into electron donating group. As we've learned already, NO2 can be easily converted into NH2 by Clemmensen reduction reaction. Now we went from electron withdrawing group to electron donating group. While electron withdrawing group was a meta director, now your electron donating group is an ortho director, okay, and para director. So our substituent would prefer to go on para position because of the steric hindrance. Our substituent is the carbonyl, so we would like to put it onto para position, but in the product, it's on the ortho position. So we have to wiggle the outcomes of this reaction and protect the para position first. We know the conditions for that, for putting a protective group on, bulky protective group, and we will sulfonate our ring. Remember the conditions here is fuming sulfuric acid. Now the para position is taken, and we can put carbonyl onto ortho position. Let's recall the conditions for that. as long as your carbonyl compound carries actual ketone functional group and not the aldehyde, you can go with Friedel-Crafts acylation. In this case, we're going to use acetyl chloride, right? And aluminum chloride as a catalyst. Okay, excellent. Now we have our para position protected. Our substituent placed the next substituent onto ortho position, which is taken now. At this point, we can actually get rid of that protecting group. So let's do just that. And to do that, we just have to use dilute H2SO4. Okay, we're almost there. Let's not forget to tag the carbons so we will not forget and look back at these groups. This is, we have our electron donating group, and we have to turn it into nitrile. We remember that the Sandmeyer's reaction will let us do just that. So we're going to first react our amine with sodium nitrite and hydrochloric acid. We'll form diazonium salt, which is an electron withdrawing group. Okay, and then it will be converted into nitrile by reacting it with potassium cyanide. And that will give you the outcomes of the reaction. Okay, we're going to run one more example, and I'll leave you alone with the practice problems. Okay. Let's see if we can come up with good reaction conditions for this reaction. Again, when I look at my substrate, on the only substituted carbon, I have an electron withdrawing group, nitro group. In the product, I still have a nitro group. So let's tag that. And then I have a hydroxy group, which is residing right next to this substituted position on the ortho carbon. Okay, let's see if we can provide good conditions for it. My electron withdrawing group is going to be a meta director. There is no way it can put hydroxy group directly onto the ortho position. And if we have not covered the NAS reactions, we would say, well, impossible to do this, okay? But now we have done that. So we understand that with NO2 being a deactivator in EAS reaction, it will send the substituent on the meta position. Let's do that. What should be the substituent? I'm putting a hydroxy group in the final product there. So my substituent better be a good living group. So I'm going to go ahead and in the first step, react my deactivated benzene ring through bromination or chlorination, doesn't matter that much. And my bromine will go onto the meta position. Okay? So let's see what will happen here. conditions. We're going to add bromine, aluminum bromide. And now we put bromine onto meta position. Let's think about the next step. If, and I'm going to pick up the laser pointer, if I said, well, I have electron withdrawing group and the leaving group meta to each other, if I add sodium hydroxide at 350 degrees Celsius, as we just learned, what would happen? My hydroxy group will not go on meta position, but will go on ortho or para position. And when I look at my reaction conditions, my ortho position is going to reside right next to nitro group, or para position will be further away from it. So if I decided to use those conditions, my major product would be this. But that's not the product of the reaction. It's not the target molecule. So how can I divert from there? Not desired product. Okay, how would I divert from these conditions? All right, let's take a look at this product and dance from here. Now I have a strong electron withdrawing group. I have a weak electron withdrawing group. So this is strong deactivator, meta director. This is weak deactivator, ortho para director. So I'm going to take advantage of it. If it's an ortho para director, and if I want to protect this position, okay, what can I do? We already know that a great protecting group will be to put a sulfonyl group on. With my bromine being much smaller than NO2, my sulfonyl group is not going to go onto this position, way too crowded, is not going to go onto this position, because I have an NO2 here, so it will be forced to go right here and protect that place, okay? So, and if we do that, let's recall the conditions again. Fuming sulfuric acid. We now will have our para position protected, or blocked. And the only way I can proceed with my elimination addition reaction is if I put the hydroxy group onto ortho position next to the NO2. So in this case, and let's remember the reaction mechanism, it will be this bond that will become triple, and then our substituent would like to go on ortho position right there. It has no other choice. It cannot go over here. Cannot go here. This is taken. So we will put hydroxy group on. Our protecting or blocking group is still on. We're almost home. We have this position taken. We have this position taken. Both of them are functionalized with the right groups. All we need to do now to go from intermediate to the final product is to remove the blocking or protecting group. So we're going to use dilute H2SO4. And that will take care of the problem, okay? So for your practice, I'm going to put several scenarios where we will start with the naked benzene ring, and I'll put a bunch of products, a bunch of reaction conditions. Your job will be to predict the product of the reaction for each step and draw the final product. And I'm not going to give you practice on that because we've practiced on those problems already several times. Practice problems. There we go. Your list might be very long, so get ready for that expansion. Mm. This is problem number 1. And let me give you one more. Mm-mm. What else do I want to do? And of course, as usual, I don't know how to count, so 4, 5, and 6. These 2 problems should be good enough for you guys. Please work on those problems. Please help each other through the discussion board, and I will see you next time. Thank you for watching. Bye-bye.